Good morning or good afternoon, everybody. Mr. Goodrow coming to you from the home studio to do a couple notes. We have section 9.1. We're going to be talking about the geometric mean and the altitude. So make sure you have your notes out and we'll get started. All right, we are talking about the geometric mean and the altitude. These are both ideas that come from our understanding of what are called right triangles. You've all dealt with right triangles. That is when you have a triangle with a 90-degree angle here. We have a couple pieces. These are called legs. So that's one leg, that's the other leg, and this is the hypotenuse. This is a right triangle because this is 90 degrees right here. We talked about Pythagorean Theorem, so all the times we've done this, it's always been on a right triangle. What we're talking about today is the geometric mean and what's called the altitude. So the altitude is a line that goes from this corner up to the hypotenuse, and it hits the hypotenuse with a 90-degree angle. Now there's only one altitude in every right triangle, and so this is just an approximation, would go from here and hit here. Most importantly though, it makes a 90-degree angle. So this is the altitude. Once we do have an altitude, it's going to do something very interesting to the shape. It's going to cut our hypotenuse into two separate pieces. So we'll have one piece over here, just call that A, and then we'll have another piece, we'll call that B over here. So the altitude cuts our hypotenuse into two pieces. So, and then how about I'll do this. I'll make a big indication just so we know we're still talking about the whole hypotenuse, and the whole hypotenuse will be called C. So there's a couple things we know just from simple addition, subtraction things. Let me undo all my markers so I can use them quickly. For example, we know this. We know A plus B equals C. And what that is just saying we cut the hypotenuse into two halves, or two pieces. They're not exactly half all the time. Two pieces, and those two pieces add together to get to the whole thing again. Well, here's my altitude right here. Call it H. And what's going to happen is if I wanted to know what my altitude is, I can actually use these pieces. And we have to use something called the geometric mean. Let me come back to this page in a little bit. So, geometric mean. Let's talk about that. A geometric mean is kind of like another mean. When you hear mean, you probably think of average. To be fair, that's actually only one type of mean. So, we have something called the geometric mean. The geometric mean. So the geometric mean is one type of mean. It is one type of way of taking a couple numbers and finding something out about them. So when we've talked about the average before, that's actually the arithmetic mean. Arithmetic mean. And that was where we take two numbers, we added them together and divide by 2. That's not what we're doing in 9.1. Excuse me. So, we are not using that one in 9.1. We're using the geometric mean, which is similar. So instead of adding two numbers and then dividing by 2, what we're going to do is we'll take two numbers, let's say a and b, and we're going to multiply them together and then square root them. All this is finding a different ratio of these numbers. It's not more or less arbitrary than this. And this has a lot of uses, a lot of things that show up in life. At the end of this video, I'm going to show you a way that this shows up, especially in some of the things I do when I'm not teaching, but some of the stats that I use. So this is the geometric mean. Multiply two numbers together and square root. So let's do an example. So an example would be the geometric mean of 7 and 10. 7 and 10. Well, if we did the arithmetic mean of 7 and 10, if we did the normal average, the thing we've done before, we get something like this, and that should be 8.5. That'd be 8.5. But the geometric mean of 7 and 10 is going to be 7 times 10 square rooted. So the square root of 70, which is going to be square root 70, and that's approximately 8.36. So you can see it's not the same answer. A geometric mean and a normal average, a normal mean, they're not going to be the same thing. They're just a totally different process. Luckily, it's just a very simple idea. It is the square root of the two numbers multiplied together. So going back to what we were just talking about, we have our hypotenuse. We have broken into two parts. We have our altitude. Our altitude is going to be the geometric mean of the hypotenuse. So if I wanted to find the altitude, it's going to be the square root of a times b. This times this equals this. So let's do a simple example and see if we're on track. Okay. I'm just going to draw a right triangle. Let me switch pens real quick. All right, we have a right triangle right here. And let's say the altitude somewhere like right here. Just for practice, I'm going to call it A. I'm going to call this H1, H2, so hypotenuse 1, hypotenuse 2, and then the whole thing is going to be just H. So that way I can find pieces. I'm going to add some variables or some numbers. So I'm just going to make these up right now. We can practice that way. Let's say this is 12 units long right here. So from this point all the way down here is 12 units long. And then let's say the other one is, what does that look like? Maybe 4? Let's say that's 4 units long. So all I have to do to find the altitude is this. It's going to be the square root of 4 times 12. Once again, it is the geometric mean of those two pieces. And the geometric mean is multiply the two numbers together and square root it. Well, 4 times 12 is 48. Square root of 48 is going to be a little less than 7. And I will round that to 1 decimal place for right now, 6.9. So we can assume this is close to 6.9. Well, we can actually work backwards. So let's say, for example, we had 6.9 and 4. If we just had these two and we were looking for 12, it isn't going to change our equation. We would do something like this. 6.9 equals the square root of 4 times h2. So if we don't have one of the pieces of the hypotenuse, all we have to do is leave it as a variable. To solve this problem, what we're going to do is square each side. When I square this right side, the square root's going to go away. So 6.9 squared is 4.761. I'm going to just make it 48 just so we can kind of match it up with this one. It's not exact, but we always have to worry about decimals and kind of where do we cut off. And we get this, divide by 4, divide by 4, and I can get 12 that way. So either way, no matter what piece we have or don't have, we can work backwards and find it. The altitude from this corner to here, that is a line that goes from the corner and makes a right angle, is going to be equal to this times this square rooted. So let's look at another property of this right triangle, something we can use with a similar idea, more geometric means. These right triangles have a lot of things that are true about them, a lot of ideas that work with different parts together so we can find it. And we like right triangles because they're the most usable to find what piece anything is. We can find just about anything on this triangle, on a right triangle, because there's certain rules we can always follow. So let's give these some names. Something like A, B, H again, and then how about X and Y? That's next, but I wanted to do a Y. So let me see if I have any white out. Perfect. Great, Y. All right, we are going to be finding even more things. So we started off saying this. We said H equals the altitude. That's the altitude equals the geometric mean of A times B. That was the first thing we talked about. Well, I actually can use these different parts to find X and Y. And what that would be is this idea. I'm going to write the general version, and then I'm going to explain it. Square root, the close times the whole. And what this means, what this is talking about, is if I want to find a leg, if I want to find the value of a leg, what I'm going to do is take the close part of the hypotenuse times the whole hypotenuse and square root it. Take the geometric mean of the whole times the close one. For example, if I wanted to find X, that would be square root of B times A plus B, because the A plus B is the whole length. Similarly, if I wanted to find Y, square root of A times A plus B. So the leg equals the close times the whole. Let's put some numbers to it and see if we can find out what things are. Let's imagine for a moment, I'll use a color so we can follow along. If we say A is 11, and we say b is 5, we can find all the pieces of the triangle. For example, we can do this one again. This is just good practice. H is going to be the square root of 5 times 11, or 55. And we'll just simplify that to one decimal place. How about 7.4? So we can get that 7.4. If I want to find y, well, I need another value because we're doing the whole length. And the whole length is very straightforward. It's just going to be a plus b. So if I wanted the whole length of the hypotenuse, that's going to be 16 long. All right, the whole length of the hypotenuse is 16. So if I wanted to find y, for example, I would do something like this. I would do the square root of, the close part is 11 times 16. The geometric mean of the close part of the hypotenuse to y times the whole hypotenuse. So that would be 16 times 11. The square root of 176, which will be somewhere around 13.3. Not exactly. There's decimals that we are always going to be cutting off, but I'm just rounding one decimal place to help me find it. 13.3. I'll do one last one over here for x to show you what that looks like. X is going to be the square root of the close part, that's 5, times the whole, that's 16. 5 times 16 is 80. It's going to be close to 9. That'll be somewhere around 8.9, we'll say. So with just those two pieces, I can find all the things we have. Let me do one quick thing first and see if that will make sense if I explain it that way. Perfect. Okay, now, those of you who are astute in the room and maybe putting things together are probably saying that I didn't have to only use the geometric mean to find some of this. That's true. Once you have some of these, and because this is a right angle, we actually have 3 right triangles in the whole thing. We obviously have the big right triangle, we have this medium right triangle, and the little right triangle. And with all of those, I can use Pythagorean Theorem. So if I have any two sides in the Pythagorean Theorem, I can use, if any two sides in a right triangle, I can use Pythagorean Theorem. So what I can do is check to make sure these are correct by doing 13.3 squared plus 8.9 squared and getting 16. Of course, it's going to be slightly off. It's going to be a couple decimal points off because we cut decimal points here, we cut decimal points here. Everywhere we had square roots, we probably had to make a choice. But we can use those to help check and make sure it works. Once again, I can say 8.9 squared plus 13.3 squared is 16 squared. Once again, if I do that check, barring that's pretty close, it obviously won't be exactly there, because you see, if I just square 8.9, I get 79.21, not square root 80, but that's okay. We're just kind of doing a check because we know we made some cuts, and that's okay. 0.89, and then 16 squared, I'm doing it over here off camera, is 256. So 79.21 plus 176.89. I get 256.1 equals 256. That is very good, close enough. Once again, the reason these are not perfectly matching up is because we cut some decimals every time we had a square root. We had to simplify it somehow, and so we weren't able to include the infinite number of decimals we had. But every one of these, I have many ways to do it. I can use Pythagorean Theorem. I now have a way to find the altitude using the geometric mean. And I have ways to find the legs using the geometric mean. It is the close part of the hypotenuse times the whole length of the hypotenuse. All right. I will do one more quick example, and then I will show you a way that we can use the geometric mean that isn't even geometry related, that I think is one of the least boring ways, I suppose is how I'd put it. I mean, it's not exciting, but I think it is an interesting way of how it works out. So let's say, for example, that's our altitude. Often you'll see the altitude as h. That's because if you were to spin this around, it's also the height of this triangle. So it's also the height of the triangle. So sometimes you'll see it as h, x, and y. So let's do a whole nother example. I hope you, if you're watching this in class, then hopefully the sub can pause the video. If you're watching this at home, I hope you pause the video when I put these letters in. So let's say this is 6 units, and let's say this is 8 units, and we're going to find h, x, and y. So give yourself a few minutes, try to find h, x, and y, and then I will resume the work in just a moment. Okay, I'm going to begin. We have the altitude. Altitude is probably the most straightforward. It's going to be the geometric mean of 6 and 8. The height, if you want to call it that, the altitude is going to be the geometric mean of 6 and 8. The square root of 48. The average would be just 7. 48 is going to be pretty close to that. About 6.9. So this is 6.9. I'll use red to circle my answers. Oop, lost the microphone. Okay. Now to find x and y, you have two options now. You could do the Pythagorean Theorem to get y and x. You have two sides, and these are both right triangles. This would be a squared and b squared. This would be your c squared. A squared and b squared, that's your c squared. You can do that for sure. I'm not going to do that. I want to practice what I've just taught you, so I'm going to show you the other way. So I'll do x right below. If you remember, x is going to be the square root of the close part of the hypotenuse times the whole hypotenuse. The whole hypotenuse is going to be 6 plus 8. So that is 14 total. Right? That's 14, 6 plus 8 to be the whole hypotenuse. 6 times 14 square rooted. The close part times the whole. 6 times 14 is 84. Well, when I type that in, I know I should get a little bit above 9. 81 is 9. So let's see what I get when I put 84 in here. I get about, I'm going to call it 9.2. What I actually got is 9.16515139. I'm going to say that's 9.2. Once again, we have to make concessions if we are simplifying radicals. Perfect, 9.2. Now, I actually have a third way I could find y. I could solve the Pythagorean theorem for the big triangle. I could solve the Pythagorean theorem for this triangle, or I can do the leg theorem. All of those are equally true. I'm going to do what we just talked about because I want to keep showing you the new thing instead of reinforce the Pythagorean theorem, because I think you guys have done it a lot. It's going to be 8 times 14. And at this point, we can already assume it's going to be bigger than 9.2 because we did this to get 9.2. So if we raise one of these numbers, it's going to be bigger. So we're looking for a bigger number than 9.2. If we do this and we find out that it is smaller, we'll go back and double check our work. 8 times 14. That is the square root of 112. I don't know what that is off the top of my head. More than 10 for sure. 10.6. 10.6. And just like we thought, it is bigger than 9.2. We'll call it 10.6. I'm simplifying all of these radicals to one decimal point. Let me see if you can see my calculator, so I'm showing you what's going on. So if you see here, I got 10.583000524. I'm just going to shorten that to 10.6. In some classes, they may ask you to do more. They may say, you know, I want 2 decimal places. I want you to do this many if you have this. In this class, let's just say 1 decimal place is good enough. So those are your 3 answers. I can always check the 2 legs by doing something like this. 10.6 squared equals 14 squared. Well, I'll plug that in. 9.2 squared plus 10.6 squared. 197, exactly actually. And 14 squared is 196. Once again, hear me when I say this, because this might be a little confusing. This is okay in this class, in this chapter. This chapter, we have to make rounding choices. And we can't keep every decimal, or else we'll be writing for eternity, literally eternity. So we have to get in the ballpark by keeping 1 decimal place, because it would be a lot different if it was 9.0, but we'll keep 0.2. So this is good enough to show that these 2 do work, and you can check all of these with Pythagorean Theorem. All right, last thing before we wrap up, I want to talk about the geometric mean and how I actually use it. One way I use it is in fantasy football. There's a way to, the reason you like geometric mean is because it can compare stats that aren't the same. For example, we have 2 quarterbacks. You can just add in the names here, and I've given them some fake stats. Fake stat number 1 is yards per game. Let's say this quarterback is averaging 184 yards a game, and this quarterback is averaging 232 yards a game. Okay, quarterback 1, though, is averaging 2.2 touchdowns a game, because it's an average. That's how it can be a decimal. So averaging 1.8 a game. And the question is, which quarterback is better? Which quarterback do you want to score you the most points? Of course, we're forgetting the idea of like how much is a yard in fantasy. We'll say touchdowns. Let's just not say any specifics. So what I'm going to do is, if I want to compare 2 things that aren't the same units, basically, I have to use the geometric mean. If I took the average of these 2 numbers, it wouldn't really make sense, because this is so small and this is so big. I'd just get a number that doesn't really work. So if I want to find out maybe a football score, we'll just name it that. I can take the geometric mean. This works for reviews on Amazon when you have different, some websites use thumbs up or thumbs down. You can take things that don't have the same stat and compare them to each other. So the number I'm going to get is not going to be a number with a unit I can use. Once again, I can't use this unit in anything. It's not going to be like any yards per touchdowns per game or anything. It's just going to be some kind of made up score we have. That's why I called it football score. So the geometric mean has a lot of uses. Also in the finance world, we won't talk about that because, to be honest, I don't totally understand finance world. But, all right, so I got 20.12. 20.12. And that number doesn't mean anything by itself. It doesn't matter what his score is. It only matters how they relate. So if he has a better score, in theory, in our little system, he's a better quarterback. We can change these if you wanted to make it more tailored to how your league scores, but this would be 20.44. So, judging by these stats, if we cared about these alone at equal weight, we actually want QB2. He's got a bigger number, a bigger average, geometric average, than QB1. So, that's one way geometric mean shows up that isn't in a triangle. I think it's a really interesting idea. But yeah, that's the geometric mean. If something wasn't clear, make sure you go back, rewatch it. I'll also try to upload the books videos as well. Those might be more helpful or less helpful, I'm not sure. But I wanted to talk about this and make sure you guys were in the know. All right, thank you very much. Good luck.